Have you ever stopped to think about the invisible science that makes your smartphone screen so tough, or how modern tools can last so much longer than they used to? Well, we're surrounded by these incredible high-tech surfaces, and today we're going to pull back the curtain on the amazing technology that creates them literally one atom at a time.
All right, let's start with a little question to get your brain working. You've got a microchip, right? Super delicate, incredibly complex. Then you've got a heavy-duty drill bit made for pure brute force. They couldn't be more different. Or could they? Turns out they share a secret.
And there you have it. The secret ingredient is an ultra-thin, high-performance coating. A film so precisely engineered that it gives each of these objects their incredible properties. We're talking about surfaces designed on a scale that's almost too small to even comprehend.
So how in the world do we make these surfaces? Well, the tech is called Physical Vapor Deposition, or PVD for short. And honestly, the best way to think about it is like painting with atoms. Instead of using a brush and paint, we're building a new surface, atom by atom.
You know, at its heart, PVID is a pretty elegant idea. You basically take a solid material, turn it into a vapor of individual atoms, and then you let those atoms land and build up a brand new, perfectly smooth layer on whatever you're trying to coat. And in this world, that target object is called the substrate.
But here's the absolute key to the whole thing, the secret ingredient, a high vacuum. Why? Well, think about it. You can't have those tiny atoms crashing into air molecules or dust on their journey. The vacuum creates a perfectly clear superhighway for our atomic vapor to travel, which means the final coating is unbelievably pure and uniform.
No matter how complicated the machine looks, the whole PVD process really just boils down to these three steps. First, you vaporize your source material. Second, those atoms travel through that vacuum highway. And third, they land and condense on your substrate, building that perfect thin film. Vaporize, travel, condense. That's the mantra.
Okay, so that first step, vaporize. This is where things get really fun. I mean, how exactly do you turn a solid chunk of, say, titanium into a cloud of individual atoms? Well, you've got two main paths you can take. We can call them the boil method and the blast method.
And this lays it out perfectly. On one side, you have evaporation. It's pretty much what it sounds like. You just heat the source material until it literally boils into a gas, kind of like steam coming from a kettle. But then you've got sputtering, and this one is way more aggressive. Here, you're blasting a solid target with high-energy ions. It's basically an atomic-scale sandblaster, physically knocking atoms loose.
Now, while both methods are great, sputtering has this advanced version that's become a total game-changer in the industry. Let's talk about the magnetic upgrade, magnetron sputtering. By adding some really powerful magnets into the mix, right behind the target material, we can totally supercharge the whole sputtering process. And I'm not talking about a tiny little tweak. This fundamentally makes the whole thing faster, more efficient, and way more controllable. It's like adding a turbocharger to our atomic sandblaster.
So how does this power-up actually work? Well, those magnetic fields create a trap for the plasma. That's the supercharged gas of ions doing the blasting, and it holds them right up against the target. This means way more ions hit the target way more often, which just skyrockets the sputtering rate. And a huge bonus here is that because it's so efficient, you can get these amazing high-density coatings without having to bake the substrate at super high temperatures. That opens up a whole new world of materials you can coat.
This brings us to the real art of PVD. See, it's not just about applying a coating. It's about engineering the perfect surface for a specific job. And scientists have a whole dashboard of controls they can play with to design exactly the film they need.
Just look at this. It's like a control panel for creating new materials. You can carefully tune the temperature to affect how well the film sticks, or the vacuum pressure to control its purity. You can even apply a little voltage to the substrate itself to change the coating's durability and internal stress. Every single one of these variables is a lever you can pull to get a totally different result.
So what are we trying to achieve with all this control? Well, just about anything you can imagine. We can engineer for mechanical properties, right, to make that drill bit ultra hard. We can control optical properties to create anti-reflective coatings on camera lenses. We can design for chemical resistance, so a medical implant won't corrode inside the body. And we can create films with incredibly high purity and high density, which is absolutely essential for making our microchips work. PVD lets us dial in the exact property we need. And this quote from the research really just hits the nail on the head. The key to everything, to unlocking all these amazing abilities, is precise control. Things like how uniform the thickness is or the morphology.
which is just a fancy word for the microscopic texture of the surface, those aren't lucky accidents. They are the direct result of some seriously meticulous engineering. So if there's one big idea to take away from all this, it's this. PVD isn't just a coating technology. It's a fabrication technology. It takes us from just covering a surface to actually building a brand new one from the ground up with atomic precision. It gives us this incredible power to engineer the world around us.
And that just leaves us with a fascinating thought, doesn't it? From the phone in your hand to the tools that build our cities, this atomic scale engineering is already all around us. The big question now is, what comes next? What incredible new materials and functions are just waiting for us to design them, one perfect atom at a time? Thanks for joining me.